This is a shift register. It's a simple electronic microcontroller with a variety of uses focused around having greater control of your electronic output pins. When you want to control lots of different outputs from a centralised place, a shift register can be a really powerful component to help you do that. I'm sure you've all seen the videos of those epic Christmas light displays where all the lights flash along with the music at different times. Stripped down to its simplest form, a task like that is actually managed by shift registers. The benefit of a shift register is the capability to manage many different outputs whilst only having a few inputs. This means you only use a fraction of the amount of output pins on your device. The specific shift register that I'm using today has 3 input pins which can then control 8 output pins, and this is how it works. For this project I'm using the 74HC595. You can find a link in the description to this or any of the other electronic bits I'm using in this project. For the purpose of this graphic, we will ignore the pins with a constant input or output, leaving us with the data, latch and clock pins, along with 8 output pins. Imagine we have 8 LEDs, one associated with each of the output pins, and we want the output to look like this. First 2 LEDs turned on, the next 2 turned off, the next 3 turned on, and the final LED turned off. We could present this as 11001110, assuming 1 means on and 0 means off. Let's use this and work through how you would tell the shift register that you want to output this pattern. The first output is a 1, so we set the data pin to on to signify this. Whilst the data pin is set to on, we will then cycle the clock pin by setting it to on, then setting it to off again. The data pin tells the shift register that the first value is 1. Then the clock pulse says to move on to the next output, essentially locking in the first 1. The second output also needs to be 1, so whilst keeping the data pin on, we do another clock pulse, locking in the value of on for the second output. Our third output is different. We want the output to be 0 or no output, so the LED will not be illuminated. To do this, we set the data pin to off and then perform another clock pulse, locking in the value of 0 on the third pin. We do this once more for the fourth pin, another clock pulse while the data pin is set to 0. Our fifth pin needs to be on, so we turn the data pin on before the next clock pulse. Then we continue doing this, matching our desired outputs until we have locked in all of the output pins and pulsed the clock after the final one. Now we set the latch pin to on. This confirms we're happy with the outputs, which are then published. In our instance, these outputs being on means that our desired LEDs will also be turned on. Of course, when we're ready to change the pins that are set to on, we simply turn off the power to the latch pin and we can start the process again. Looking at how the Raspberry Pi wires up to the shift register, I've used the design shown on the screen right now. As you can see, each of the output pins of the shift register are connected to a 330 ohm resistor followed by an LED. The VCC and MR pins connect to the 5V pin of the Pi for the power, with the OE and ground pins connected to the Raspberry Pi ground. This leaves the data, latch and clock, which I've connected to GPIO 16, 20 and 21 respectively. If you like, you can use a breadboard for this, but because I know what I'm going to use this for, I'm going to solder straight to stripboard. I'll leave a link in the description to the soldering equipment that I use. I'll start off with a new Python file that I've titled shiftreg-basic.py. As with any project using the GPIO pins, you have to import the library, which I've done, and then set the mode to BCM. Next, we declare a variable for each of the data, latch and clock pins. I set the value of each of these variables to match the pin number that they are connected to. After using the setup command for each of those pins, I then declare an LED pattern. I've used an 8-character string for the LED pattern variable. We can associate each character of this string with one of the outputs. This way, if we have a string of all zeros, that would be all LEDs off, and all ones would be all LEDs on. I'm going to use the pattern 11001110. You can see I accidentally missed off one of the zeros, but I went back and corrected that after. First off, I set the latch pin to 0. This means the data and clock pins will be in a receptive state. As there are 8 LEDs, I'll declare a for loop that iterates 8 times. You can see there are 3 actions each time it iterates through the for loop. First, it sets the data pin. It sets this to either a 1 or a 0, depending on what character in the string it's referring to. The next 2 lines are turning the clock pin on and then off again as a pulse. Finally, I set the latch pin to on. This locks in all 8 values. After saving the code by pressing Ctrl and X and then Y, I run the code with python shift-reg-basic.py. And just ignoring those warnings on the screen there, you can see in the bottom corner how this looks on the circuit that I wired. We don't just have to have 8 static outputs, we can actually loop through and keep on changing what output pins are on. I'll start by creating a new Python file called shift-reg-sequence.py this time. In the same way as before, I'm going to import the GPIO library, set the mode to BCM, and declare the values of the data, latch, and clock pins. Of course, you also have to set up each of the pins with gpio.setup. Because we're going to loop through the outputs on a timed basis, I'm going to import time as well. I'm going to declare an outside loop using for I in range 10, and this means that it's going to loop through 10 times. Within this loop, I'm going to use a custom function called setOutput, and within that I'm going to pass the pattern that I want the LEDs to display. Between each set output, I'm using time.sleep 0.5 to wait half a second before changing the output. As you can see, this loop will alternate between half of the LEDs being on and then the other half being on, and it does this 10 times. And then just after the for loop, I'm going to set the output to all zeros to turn all of the LEDs off. Of course, we have to define the function of set output, so I'll do that just above the for loop, and we pass in the LED pattern here. The setOutput function is going to look very similar to the previous exercise that we did with just a single output. So within here, like before, we're going to loop through 8 times, once for each LED. We refer to the LED pattern variable here, which has been passed in. So just looking at how this for loop works, the set output 01010101 is going to be passed into the set output function, and it's going to run through this function here, setting the pattern of the LED to that. Next, after a half a second pause, it's going to set the output to 10101010, and it's going to do that using that same function, but using a different LED pattern. Obviously, it loops through this 10 times before then turning all the LEDs off with the final set output. Again, I'll save this with Ctrl and X and then Y to save, and I'll run that in the same way with python shift-reg-sequence.py. Just ignoring those warnings again, you can see that this makes the LEDs alternate between on and off. If you need more than 8 output pins, you could even use one shift register to output 6 of its pins to the data, clock and latch pins of an additional 2 shift registers. This will give you a total of 18 pins output. There are lots of uses for shift registers, many of which involve LEDs. I'm going to use the shift register that I soldered as the foundation of an electronic dice project, which I'll show in my next video. If this video was useful, please consider giving it a like, and of course, if you want to see more like this, then feel free to subscribe. Thanks very much for watching, and I'll see you in the next one.